Welcome to AMS on the Air. I'm Jeff Rosenfeld.
I am Irene Sands.
And I'm Dakota Smith. We're ready to podcast about all things weather, water, and climate.
The last thing you want is heavy rainfall falling with the dome open and 30,000, 40,000 patrons there, including the owner of the team. You don't want that happening. That's the key. That's where the real value is. It's not in just a number that comes out. It's actually providing that whole envelope of information that decision makers actually need.
So this episode we're talking to Paul Roebber, who's a professor of atmospheric science at the University of Wisconsin Milwaukee, although I think he's also listed as a professor of mathematical sciences, which may explain a little bit about what's interesting in what he does. He's a professor of who's been really interested in all sorts of topics that relate to forecasting and storms over the years. But the thing that really has been distinctive in recent years about his work seems to be his interest in taking artificial intelligence and applying it to various meteorological problems, and specifically in forecasting. And I got really interested in what he does because I'm kind of fascinated by this idea that some of this artificial intelligence or this machine learning, all these different topics are just exploding on the scene. And at the AMS meeting in Phoenix, you could see that in the program. There's just more and more topics that are coming up in using the techniques of machine learning and artificial intelligence. And Paul's been at the center of that. And in particular, recently, he's been working with what I guess you would say are some of the equations and techniques of modeling evolution in species in biology and applying that to ways of looking at weather data and trying to get models to produce better distributions of outputs and things that forecasters can use to be more characteristic of the actual possibilities in the atmosphere. So these are really interesting intersections between fields, and he's at the center of that. And of course, mathematically, the linkage is very clear, but I think it's pretty interesting that such linkages can be made. So he gets his techniques from a lot of different places and puts them to use, and so that's one of them. The link between evolution and meteorology alone, I think, is very interesting. But the other thing that Paul was talking about in Phoenix, where we interviewed him during the annual meeting, is this notion that there comes a point where artificial intelligence might take over so much of the job of producing forecasts or improving on the use of the statistics, etc., that there's less of a role for human beings in the forecast process. And as we all know, we're big fans of human beings, partly because we are humans, I guess, right? But that's what meteorology has been for so many years. So this has been a problem that's been around for a really long time. And in his presentation at the AMS, Paul actually went back to a concept from the 1970s that was in a paper, I think it was in BAM's 1977. Len Snellman had introduced this term called meteorological cancer, which referred to the problem where if forecasters rely so much on the automated guidance, they kind of atrophy like the cells that are afflicted with cancer and no longer perform their function well. And even though the automation is getting better and better, the forecasters are getting worse and worse and worse, in a way, less practiced at what they do and less vigilant. And you get this problem where you might actually be inhibiting the progress that is possible using artificial intelligence wisely. So Paul was addressing that at the conference as well. And in fact, his first image in the presentation was of the autopilot in an airplane. And what it was this inflatable doll sitting in the pilot's seat. And it was taken from the movie Airplane way back in the 1970s. I don't know if you've seen that or not. You remember that one, Irene? Or no, pretty funny movie. But anyway, it was this inflatable doll that was the autopilot. Anyway, it was a funny image, and just kind of reminds us that you can't just stick anything in the pilot seat, even in meteorology. So I'm just wondering if you guys have had any interaction with the automation process where you feel like you're kind of getting dissociated from the meteorology that you actually love to do.
From a broadcaster's point of view, I think right now, okay, we automate, let's say, the warnings and the watches as soon as they're issued. And that's great because that's work that it's done automatic, and you don't have to take time from watching a severe weather cell or from forecasting, and you can still inform your viewers. Now, the issue that I have is when but my pet peeves are like when an on-air meteorologist just solely relies on what the model says and not on their gut feeling or their knowledge. And I've seen it more often now across the board, across most of the stations. You can see the meteorologist saying, well, the Euro says this and the GFS says this. And then they don't tell you their forecast. Have you noticed that, Dakota?
Yeah, I have. It's sort of like displaying all the scenarios, but then not actually giving you a forecast.
Exactly. So you're sitting there, you're waiting, and it happened to me recently. I heard the meteorologist say, okay, yeah, this is a Euro. The Euro calls for so much rain in here, and then the GFS is hardly any rain. Well, in the 5-day forecast, we have this, and that. And it's like, okay, then which one is it? And I put myself in the viewer's shoes. And I'm like, wow, that's what's happening here. Why didn't I get the forecast? And it's rough because you have all these models and then you also have management on top of you saying, well, show all the models because, the other station's doing it, or show all the models because now we subscribe to this vendor that it's providing all the models, whatever reason it is that they're telling you to show all the models. And then you don't show the forecast. So in that aspect, I think there is a lot of meteorological cancer going on.
That also goes back to something that Paul talks about a fair amount, which is that machines and algorithms, artificial intelligence, just not good at understanding context. They don't get that at all. That's not what they do. So every day, I mean, this is why meteorology is so incredibly interesting too. So every day is a different context. You cannot do this kind of work and not be very attuned to the context that is the day's atmosphere or how people are using it. What are people doing that day? Everything is different every day, and you can't ignore it. So I think that's a great reason to listen to Paul, because he's one of these people who really understands what's good about artificial intelligence, but he's also really good at understanding what its limits are and how to teach his students around it too. I think he's got a great program there at the University of Wisconsin where he's getting students out to actually interact with clients on a one-to-one basis, which is another story another time. But this is somebody who can see both sides of the issue really well. So I think this is a good opportunity let's take a listen and hear a master describe what this is all about.
My research interests are very eclectic. And so unlike a lot of people who dig very deeply and narrowly, I try to dig deeply, but broadly also, and more just not thinking that I know everything about everything, and so trying to read widely and pick up ideas from other disciplines, which may not be obviously directly applicable to the kind of work that I'm doing, but I see a connection and then I run with it. The latest version, I've always been interested in some version of artificial intelligence since the 1980s, actually. And if you're familiar with what those systems were, they were called expert systems. Effectively, what they did is they sat down, they interviewed an expert, and they tried to codify the rules by which they made decisions. And then they would put that into a program and run the program. And they found that they did reasonably well, but really didn't achieve the level that was hoped for. And so things kind of hit a roadblock at that point and really didn't progress too much until back propagation with artificial neural networks was developed. And that was, I think, the late 1980s, early 90s. And at that point, artificial neural networks started to come online. Effectively, what they are is all of these techniques you can think of just as mapping inputs to outputs. So it could be anything. What I do is weather data and mapping some sort of set of inputs to a particular forecast output. That's one way you can do it. You could map a set of inputs to world events if you wanted to. What's the risk of a political overthrow in this country, which I know the Department of Defense is actually doing. They're trying to build these huge models of world events and trying to predict where the risk factors really are. And that's another application of machine learning, which is what everybody calls it now. It's really the same thing as artificial intelligence, but because of that roadblock in the 1980s, I think it's been relabeled. And I think that relabeling is appropriate because it really is a different set of techniques than it was in the 80s. But you'll see these terms kind of used interchangeably. And really what it means is it's you're using a computer to train algorithms on a set of information to produce some sort of result. And that's a very broad statement, but that really covers the wide range of things that this is applicable to. In my particular interest, really, I started doing artificial neural networks in the late 1990s, and I started on it when I was looking at forecasting snow depth and just being driven crazy by the 10-to-1 ratio, which I don't know if you're familiar with that, but 1 inch of liquid equivalent equals 10 inches of snow. And if I live in the Midwest now beside Lake Michigan, and we know if we get a flow off Lake Michigan, then the snow ratio is more like 30-to-1. It's really just light, fluffy stuff. If you get a storm that comes from, say, the Texas Panhandle or Oklahoma, then it's going to be like 3 or 4-to-1. It's concrete.
I would think it's the other way around.
No, it's so heavily laden with moisture that
even from a long pass over the plains.
Yeah. They tend to be very, very heavy rainfall producers, or if it's cold enough, it'll be snow. But there's so much moisture content in it, it just doesn't have the fluffy characteristics.
So it doesn't pick it up as much when it has a brief pass over the lake.
Well, it tends to be cold, really cold air conditions also, and so there's one of the problems with the old techniques. And I did some research on this. I found out that the 10-to-1 came from a late 19th century study in Toronto of about 10 storms. And they were kind of all over the place in terms of what the ratio actually was that they measured, but they said, it averages out to about 10-to-1. That's a handy number.
Maybe the average wasn't the right number.
And everybody just glommed onto that because 10-to-1 is a very handy number. And it turns out it's not a very appropriate way to do it. And people realized that somewhere down the line, and they started various attempts to correct it, mostly using things like surface temperature, which is a first-order correction that's useful. It's very important, but it's not enough because if you think about what makes a snowflake, it starts up there. Mm-hmm. And it's going through a whole process with all kinds of changing conditions, and it comes down here. So it turns out that the surface temperature is not nearly enough to actually reproduce what the snow ratio is. And so I said, well, obviously you need some sort of profile information. So I started collecting radiosonde data, and I used an artificial neural network, actually an ensemble of networks, to train against snow fall data that I collected from a series of stations around the United States, east of the Rockies all the way to the East Coast. And I found that with the neural network, you could actually produce a relatively useful technique. Now, there's a lot of noise in snow depth measurements, and because of that, I had to do a little bit of averaging. So effectively what I did was broke it down into classes where you had very heavyweight snowfall, that would be one class, then sort of the middle range, and then the very lightweight snowfall was the highest range. And so I published that in a paper, and I got contacted by a weather service office, and they said, this is kind of interesting. We'd like to implement this at our office. And so it was completely informal research. We built a website. They had a really good web developer there. So he worked with me, and I shared the the formulas, and so he was able to implement that all and code it up. And so now you can go, and this page is still active, so you can go there and you can click on any National Weather Service site and get a forecast for what the snow ratio probability will be in those 3 different classes. And it uses model data, the latest model runs, and you can look back through a series of model runs, and you can actually change the inputs. If you don't believe the model, if you think it's going to be a little bit different, you can change the most important factors related to snow ratio to see how that changes the forecast. And so they were using that routinely at that Weather Service office, but of course anybody could use it, and it's open to the general public too. And I used to get a lot of, I always knew when it went down because all of a sudden I get all these emails, hey, what's up with the snow ratio site? I say, oh, okay, let's fix that. But I also got contacted by the Weather Prediction Center a few years after that, and they said they're kind of interested in this technique. We'd like to test it out. So they implemented a test version of it at WPC, ran it against a bunch of other techniques, and discovered that it works really well. So it's still part of the national guidance that's produced for snow ratio. So that was my first success with machine learning.
There are a lot of interesting things you bring up. One of the interesting things about your talk is you talked about autopilot, AI
Yes.
autopilot.
Right.
And I'm thinking that could apply either to the AI or to the human managing the process or making the decisions. So
It can.
maybe you could explain what you meant by autopilot.
So
AI.
actually, Leonard Snellman was a meteorologist, and in the 1970s he published a paper and talked a lot about this, which was at the time that multiple linear regression was first came out. It's what we call MOS, Model Output Statistics. It's basically multiple linear regression. And it's a tool that people can use to make forecasts of things like maximum minimum temperature and probability of precipitation, stuff like that. And it's very useful. In a lot of situations, it's hard to beat. But there are plenty of situations where it's not hard to beat, and you have to recognize the difference between those two. Furthermore, the weather decision context is about a lot more than just what the temperature is going to be and whether or not it's going to rain or anything like that. There are many more other factors that you have to take into account. And from a National Weather Service perspective, it's about public safety first and foremost. And so that's a much bigger issue than just forecasting temperatures and things like that. So Snellman argued that we were at a risk of developing meteorological cancer. That's what he called it. And what he meant by that is that if you become too reliant on a useful tool like that and don't continue to be engaged in the forecast process, your skills will atrophy. And at some point, when you don't have that guidance, or that guidance is out to lunch, which does happen, you won't be able to intervene and actually correct it. So that's sort of the person being subjugated in some sense by the automated guidance and just believing it for lack of any skill in doing anything otherwise. And that's definitely a risk, especially when you overload people with forecast tasks. They have too much on their plate, then it's very easy to think, okay, I'll just go with the MOS and do that kind of thing. So that concept, that fear has been around for a long time. I actually think it's a very valid concern because, and we know from the airline industry, the same thing is true, that they've been using autopilot for a long time now, and they work really hard to have the pilots maintain situational awareness because autopilot is very good, but it's not perfect. And there are situations that arise when you're flying. You definitely want somebody there who can take things over if things are going awry. And so they have to figure out ways to keep the pilots engaged so that they're not just lulled to sleep by the autopilot. So this is very much the same problem that we have.
How do you keep the forecasters engaged then?
I think by leveraging the tool. And one of the ways that I do that, a lot of machine learning approaches can be viewed as a black box. So stuff goes into the black box and then out pops some result. But it doesn't have to be that way. You can actually set up methods to interrogate the black box. And so to understand where the sensitivities are in that forecast. An example I use is when I use an artificial neural network to produce a forecast of something. Let's say it's rain. There's a lot of inputs that go into that, and then there's a probability of rain above a certain threshold that comes out of it. So let's say you come out with a 65% chance of more than 2 inches of rain in this location at this particular time. Well, that's a pretty alarming number, 2 inches of rain. But as a forecaster, what you want to do is say, okay, where's that number coming from? What's driving that 2 inches of rain? And what we discovered when we actually did train neural networks to do this, one of the most important factors is the layer average specific humidity, which is a measure of the moisture content of the atmosphere. So you have more moisture, you have a much higher risk of having these really heavy rainfalls, which makes a lot of sense. It's just how much moisture you can squeeze out of the atmosphere effectively. And so it's very sensitive to that. But let's say you're in a situation where it's coming up with a 2-inch rainfall. You know, based on your analysis of the situation, it's because there's this, in the forecast, there's this plume, very, very localized plume of high moisture content that's coming into the area, at least this forecast come into the area. But you may be not so confident that's actually going to arrive. Maybe you'll be a little bit less than that because the leading edge of that is staying to the south. Then what you want to see is, okay, how sensitive is the forecast to that change that you're anticipating is actually going to happen? And it's likely to be very sensitive to that. And so especially if you have a second tool that you can look at, which has a different response, and that's what we did. We actually trained multiple logistic regression models as well as artificial neural networks, and it has the same set of inputs, but it weights things differently. And so you'll see that they tend to agree with each other when there's a high probability of something happening. They tend to agree with each other. When there's a low probability of something happening, they also tend to agree with each other, but there's variation around that agreement. So what you want to figure out is what are the sensitivities that are driving that variation, and how does that reflect back on the actual situation that you as the meteorologist have figured out is actually going to happen. And that's the way you stay engaged, because then you say, okay, this is my understanding of the situation. This is what the models are coming up with based on that situation. But this one is really relying on this factor, which I have very low confidence in. This other one, which is coming out with a lower forecast, doesn't rely so much on that one. So now I'm going to go with that lower forecast because I think that's the much more reliable forecast in the situation based on my understanding of what's actually going on. So you can stay very actively engaged. It takes more time to do those kinds of things, which is also why you have to set things up so that the forecaster has the ability to do that kind of intelligent interrogation of the data if you want good performance. And if you're providing decision support, which is, again, what Innovative Weather provides to really high-profile organizations like the Brewers, or last thing you want is heavy rainfall falling with the dome open and 30,000, 40,000 patrons there, including the owner of the team. You don't want that happening. Or, for utility companies, we work with a number of utility companies, and just operational logistics are where we work with them. So they have to schedule crews in the case of outages. They have two metrics of success, one of which is how quickly can they restore the power, and the second of which is how cheaply can they restore the power, because they don't want to spend extra money if they don't have to. And they've told us multiple occasions that we save them tens of thousands of dollars on a single forecast because we're providing them the detailed communication, all of the extra stuff, the context that they really need to make those forecasts properly. So that's the key. That's where the real value is. It's not in just a number that comes out. It's actually providing that whole envelope of information that decision makers actually need.
How do we train for the future weather service office or forecaster's job in an industry so that people are going to be ready to be that sort of alert, interrogating, probing, critically thinking forecaster, but who's on autopilot a lot of the time?
Well, so in conjunction with Robert Hoffman and some other folks, we actually just this past year published a book called Minding the Weather, How Expert Forecasters Think. And we talked about some of those issues. And the main thing is there's some interesting studies that the Air Force did a number of years ago because they reduced their requirements for Air Force meteorologists to be forecasters. So basically, coming out of high school, they were training them to be forecasters, whereas before they had more stiff requirements. And they found that what they really got by doing that was they took the science out of the process. And some people are particularly good at pattern recognition and things like that. And you can go a long way in forecasting with just pattern recognition. And you can also find lots of terrific scientists who are absolutely the worst forecasters you could imagine. But what you really want is the combination of those two things. Somebody who has an aptitude for pattern recognition, a feel for the weather, if you like, but also understands the science behind it. And those are what we call scientific forecasters. And neither the pattern recognizer nor the pure scientist can ever achieve the level of someone who has that combination of skills. So that's what you need, is somebody who thinks like that. So it basically means you need good foundational training in meteorology so that you understand the science, so you can interrogate the weather situation, so that you can use the tools that come online, whatever they happen to be, to use them intelligently to actually figure out what's going on. That's a pretty tall ask, to ask somebody to have all those things. Those are really special people.
But you're not emphasizing, say, a background in computer science or AI just to understand the AI routines.
Not necessarily. I mean, I think you need people who have that understanding. A lot of machine learning actual projects use a combination of individuals with different sets of skills. The whole team has to have domain expertise, has to have computational skills, and has to have the sort of just the machine learning tools and the ability to work with that. They need all three of those things. It doesn't have to all come in the same person, but you need all three of them. If you just have the computer programming and the machine learning chops and you don't have domain expertise, you end up doing a lot of really dumb things. And I've seen examples of this where people did that, and it's because they don't understand the context of what they're trying to do. And a great example of this is if you imagine training an algorithm to do something, and it's complicated, effectively what that means is it's a multidimensional space that you're searching to try to find the solutions. And you have to find those transition boundaries in this multidimensional space. And the more multidimensional it is, the higher dimension it is, you need more data to train. So you can't just, and some people have this idea, well, let's just throw everything in there and it'll magically pop out with a solution. But no, because you have a finite amount of data. And it goes geometrically increases the amount of data that you need as you start increasing the number of factors that you put into it. So if you're throwing garbage in there, like I can try to train something for a heavy rainfall forecast and put my grandmother's cubic meters of refrigerator space in it, and I can add that, and the machine learning will eventually discount it, hopefully, but maybe not. It could find a spurious correlation, but it's wasting all of that training data trying to just get rid of the junk that you've put into it. So you need the domain expertise to really reduce that size, the space, as much as possible, without eliminating things that might have potential, which is something that requires a certain amount of sophistication to be able to do that. So there's an artistry to that also. One of the really heavy lifts for machine learning that people don't talk about much, but everybody recognizes, is what I call data wrangling, which is we've got lots of different kinds of data in lots of different formats, and we have to sync it all together in terms of time and space and just basic format that it comes in. And then you have to quality control it because you don't want to be putting garbage into it if you can avoid it. And all of that effort is all front end before you can do anything with the machine learning. And that takes a tremendous amount of effort.
That, to me, I was starting to wonder if as we enter this world where we're kind of in a big data situation, where we're grasping for all these buckets of data from cell phones and other things, depending on the situation, but dirty data, crappy data, and yet it's good because there's so much of it. But you're sort of saying that, it's to me, I'm trying to figure out, is that world more compatible with AI or less compatible with AI? Because it depends on trying to find sort of an okay solution to very large data sets rather than trying to find, say, the exact right data, but from a small set. So
Yeah.
which is more compatible to?
Well, so the big data, it's a good question. The big data, one advantage you have with that is because the data is so big, you do have more opportunity to train it in a way that you can eliminate the spurious information. And that's what you have to hope. But of course, nobody knows what the size of that space actually is. So you may think you're optimizing things, but you're actually not. And there's no answer to that. You just don't know. And the only way to get some sense of how capable it is to use independent data and run it through that system. And presumably you need to expose it to enough independent data capturing all the different scenarios you're likely to experience before you have a real sense of how useful it is. And the other thing that people make the mistake is assuming that there's no bias if it's a machine learning algorithm. Of course there's bias, because there's bias in how we collect the data. We decide these are things we're going to measure, and this is how we're going to measure it. So you've already introduced a certain amount of subjectivity into what you're doing, and then somebody else decides, a domain expert decides what's important, and you put that into it. So there's lots of bias in it. It will be very reproducible bias. It'll keep coming up with the same answer over and over and over again if you give it the same information, but it will also reproduce whatever bias is in your system if that's the way you've trained it.
We're sort of in a throwback stage, I think, to Len Snellman's era, in that there were a lot of people very anxious about the future of forecasting and the role of a forecaster. So here we are again, a lot of people trying to learn things they never had to learn before, just to stay on top of the job prospects, economic pressures pushing in a different direction. So should I be anxious about the future of human weather forecasters?
I think it's reasonable to be concerned about it, and I think if people discuss the issue openly and intelligently and don't just dig in, then they will understand that there's a lot to be gained by doing this if it's done appropriately, and there's a lot to be lost if it's done inappropriately. And you have to understand what those trade-offs actually are. There are some kinds of forecasts where it's a simple matter of automating it. There's no real cost to doing that. It makes a lot of sense to do that. You should do that. But there are many other contexts where sophisticated information is really required. And in those contexts, you want to make sure that you preserve that capability of providing it. Otherwise, you completely cut yourself off at the knees.
Well, I'll take that as hope. I really appreciate it, Paul. Thank you.
Yeah, thank you.
Thank you so much for listening to another episode of AMS on the Air. Wherever you're listening right now, subscribe to that feed so that you get future episodes whenever we publish them.
Just in case you don't get notifications, because some of us don't, you can follow us on social media, on Instagram, Twitter, Facebook, and you can see what we post there. And whenever we have a new episode, we'll throw some links there too.
So happy listening and happy weather.